Hello everyone, welcome back to the channel. So today we'll be starting tutorial on Simplorer, or also known as Twin Builder. But before that, I'm just reminding you to please subscribe the channel if you have not already, like the content if you like, and yeah, of course, if you like that to share within your peers, then you can do that too. So please do not forget to subscribe, because that's the greatest motivation, you know. Okay, now let's begin. So previously what we did was we calculated inductance values, and the matrix was created by the simulation, and the matrix that was created was for the distance swipe between the TX and RX coil, and the self-inductance value was calculated, right? So mutual inductance and self-inductance, we had these data. So basically what will happen now, what we will do now is we'll put that module, or let's say that matrix in form of a block, right, that can be used in a circuit diagram. So Simplorer in a simple terms is nothing but it's like piecing, where you draw circuits, you put blocks, or let's say like MATLAB Simulink, where you can do these things, right? So it's very similar to that. So we will build a very simple circuit, and then we'll check coil to coil efficiency, how much power is wirelessly being transferred and with what efficiency it is being transferred. So two things matter, right? So how much you are sending from sending in, and how much you are getting in the receiving side, right? So yeah, that's a simple concept, and first let's begin, and then we will discuss more on this later as we do it. So yeah, so first thing you need to have is you need to open up the coil design that we have already done previously, but you can see last time we did a little bit different design, and this is a somewhat different file that I'm opening right now. That is because I do not have the particular same file right now with me, because I did this in my laboratory and I'm not having the access to my laboratory PC, so that is why I'm doing in my personal laptop today, and that is what is causing me a little bit of delay, and my laptop is somehow slow, so please ignore that. I will try to skip that part. Okay, and then next thing is open up that file and then create a Simplorer file or Twin Builder file just by right clicking, the same process. Okay, so we select the project file and then we right click and then insert, and here it is, the Twin Builder design. Okay, so it will take some time and create a file for you that's called Twin Builder 2. Let's just rename this, okay, and call it tutorial. Okay, and here you can see it's empty portion, it's a matrix, it looks like grid, right? So just make sure that you are in the top corner, top left corner, so just go through this slider and then go to the top left corner, so that it will be very easy for you to just locate the circuit when you sometimes you miss it or do something, like it might just go away from the screen. So if you go to top left or top right corner, that becomes very easy to you to locate the circuit if something happens by chance. So yeah, that's it, and I guess I have already shown you the kind of circuit we are building. So it will be a very simple circuit that will be comprising of a voltage source, right, and we'll define the frequency there. Let's say we can work around 1 megahertz or 6.78 megahertz. Let's take 6.7 megahertz for now, right? And then we'll put our model that we calculated, the simulation that we did, the simulation of coil that we did, somewhere in the middle, right? Because it will transfer the power wirelessly, so it will act somewhere in the middle. And then something extra that will be in that model or in that circuit will be a capacitor for now, a series capacitor on both the side, on primary side as well as on the secondary side. Okay, and then other things like they are for measurements. So that's as simple as that. So let's just begin to draw. So where we will find these components is here is something called component library. Okay, if you do not find it, or you have like having a problem locating it, or then you can just go to view, and then there you see component libraries. So just check that thing, right? So yeah, that's there. So if you can't see in your screen, or if you're just missing out, or you are trying to find where it is, then you can just go to view and check that thing. And once you go, come and land here in the component library, so I have already few things here in favorites, right? But obviously you won't find these things there, and I have few things in most recently used. Again, if you're using it for the first time, you won't find these things there. So it's not that easy to find. So where does those components that we need lie majorly is on the basic elements. Here inside basic elements, inside circuit, there's passive component. So most of the components like capacitor, and then there's inductor, right, and mutual inductances and resistor. So these are few things that we might need, and then plus you need sources. So again, there is source, a voltage source, of course, right? So it's very easy here to find it. Now other things we are not concerned that much, so our work can be done based on this much things, right? Voltage source first, voltage source, and I can press escape key just to make that thing, so I can zoom in a little bit so that it will be much more visible to you. Okay, okay, I guess that's fine now. Okay. Press voltage, and then I will need a aneurysm. Okay, so somewhere here, escape, I need to rotate it. So I'm not going to circuit will work. If the socket is able, then I can do this, right? It's very easy. Okay, this is chip, what happens, and then there is voltmeter. Okay, it's fine. Okay, okay. These things here, this is good. And similarly we need, okay, it will be very easy if we place the model on the center in the first place. It will be a lot easier. So what we do is we go to Twin Builder, here the menu in the top, I guess fourth last menu, and then in the sub circuit, and you will find Maxwell component inside it, and inside Maxwell component there is dynamic magnetostatic. So in that dynamic magnetostatic, that's what we are going to, because our model is magnetostatic. It will take some time, and a lot more time in my laptop. Now what happens is sometimes you can you might be creating a different project for yourself, right? So if that is the case, then it's not the current project that you're using. So you have to do browse project, and then locate that project file, and inside that project file you will link the design here. So since I have created the the Simplorer file inside the same project file, that is helical coil, so it's by default the current project. So, and I'm not going to change that because it's the same package, right? So I'm using current project, and then inside design I will choose which one it is, right? So it's named as 3.8 mm stranded, and I will do particularly for that one. Okay, 3.8 mm stranded, yeah, I guess is the same. So yeah, and the rest of the things remain same, we do not change anything. And then here it is, the model is right here, right? So we can place it, press escape key, and then rotate it. Now you might be, it might be very confusing, which side is up and which side is down, right? Which side is what? So if I zoom in, if I zoom fit, I guess zoom in more, then maybe I can show you clearly. So you can see here's something known as rxin.src, txin.src, and then rxin.snk and txin.snk. So snk, I'm not sure, but I guess it means sync, and src means source. So by that that is roughly my guess, but I have not found anything more forming than this, right? So I guess src is source and snk is sync, and that's very close match, right? So obviously source must be in the positive side and sink must be in the negative side. So that's my take, and that's how I do it, and it's correct also. Okay, so I will just rotate it to make sure that sink goes on the downside and source is on the upper side. So yeah, that's done there. Let's zoom out and then let's connect. So you can say there are 4 terminals, so one for this side, one for the other side. Okay, yeah, that looks fine. And then let's come to the secondary side. What is remaining? Okay, something else is also remaining on the
remaining on this side, and what's particularly that is we have not placed capacitor. And after placing this, I'm going to describe you a few things about this. What exactly is this capacitor for? Okay, and make sure that the polarity is on the right side. So I guess this red dot means negative polarity, and though it doesn't matter that much, you can always swipe the direction if something happens, or like if you get phase difference, drastic phase difference, like phase difference of 180 degree, then you might have problem with the measurements, right? So in that case, just make sure that the polarity is in the right place, right? And
why a capacitor in series? And I'm doing this particularly on both sides, both on the primary side as well as on the secondary side. And why we do this is for the tuning. It's actually for the resonance. That is the C1 right now here will resonate with the primary coil, and similarly the C2, or let's say C out on the next side, will resonate with the self inductance of the receiving coil, and we resonate at certain frequency, and that frequency might be equal to switching frequency as well. So in many cases it's equal to switching frequency. So let's say we are tuning this this set of inductor and capacitor in series. It's called series topology. Similarly, we also have series parallel topology, parallel series topology, and parallel topology. Right now the simplest one is series topology, and it works, but depending on the application and needs, you can use different kinds of topologies, and the C is not necessarily be in series, it can be in parallel also, right? So what this does is this together will resonate. Similarly, secondary side will also resonate, and they will resonate at same frequency. And when this happens, we can actually send power because of this phenomenon, right? We can transfer power from one end to another end wirelessly. So there's a tight coupling, and it's called magnetic resonance coupling. So yeah, that's a simple fundamental thing that you need to understand why we are doing the series capacitor kind of thing. So let's do this for the other side as well.
And let's pick capacitor again, and then rotate it. Okay. Yeah. And then I will connect this to this side. Okay. Come on. Seriously. No, this is too much. We need another ammeter. Okay. Rotate. Well, that's good enough. And then we'll need a voltmeter here again. Okay. And then one resistor as a load. Okay. So yeah, that's it. And as simple as that, the circuit is complete, right?
Double click on the voltage source, and there is a lot of things that you can do here, but I will simply advise you not to change each and everything here right now. So what's there, just leave that in default value. Just change a few things that I will tell you. Okay, so the first thing you can do is do not go to any other tabs, because this AC parameter tab might look very familiar and you might think that the magnitude and phase is exactly what you need, but do not change anything there. Just go to parameters, stay in that tab, and okay, you can change the name, or if you do not want, let's just leave it. Okay, or let's say you want to say this is E source. Okay, that's fine. Go and select time control, and in time control it's already signed, so it's not a problem. Go to RMS value if you want RMS value input, or just if you want to check the amplitude, then you can go and change the amplitude. Let's just keep 320 volts of amplitude, so that will automatically convert it into RMS, so we do not need to worry about that. And then in the frequency, So as I already told you, we are going for 6.67 megahertz, so make sure you change that to megahertz. Okay, rest is fine, nothing to do here, just press OK, and that is set. As you can see, the logo here had changed, the icon here changed, and it's now giving sinusoidal input of 6.78 megahertz. Now since we have given all the related values right now except C in and C out, there is a few things that we need to do, like there are a few things that we can do here. The first thing is let's use variable, so that it will be very easy. When we use variables, it becomes easy to change the value and tune the circuit, and you will realize this when you start tuning the circuit again and again and again for that particular frequency. I will tell you how to do it, but before that we need to create variables, right? So C in and C out, instead of naming them here, what we will do is we'll just change it to C1, and we'll use C in here somewhere, right? Instead of the value, we'll use C in. When you press enter, it will bring this dialog, and here you can choose capacitance, right? Capacitance, I guess it will always be in picofarad range for this kind of values that we're using. It's 15 microhenry, and for 15 microhenry, while you work around with frequencies like 6.78, it is somewhere around picofarad range. So I will just leave it in picofarad, and sometime if you have to change, then you can come here and always change this setting. Okay, so for now I'm giving a random value of 100. This is random. Okay, so let's just do it. Okay, press. So the variable is created. My PC is a little bit slow, ignore that. Yeah, it's there. And let's do same for C2, and then we'll name this C out. Remember, instead of giving the absolute value, we are giving the variable name. So once we press enter, we can choose capacitance and then the picofarad range, that's fine, and 100 for this too. Press enter, it will create. So how now? Similarly for load resistance, because it might be very so let's just change this to R1 and then R load. So it is very obvious that we might need to change these values again and again if you want to test the circuit again and again, right? So press enter, choose unit type as resistance. Okay, resistance, it's an ohm, fine, 10 ohm, that's fine. Okay, now how you can change these variables easily? Now when you click here, it will give you the variable list of variables that you have created, C in, C out, and R load, and the values here and the unit here. So you can change unit from this corner and value from this. So it's very easy, and you can change like that only. Okay, it's done. It's done. It's that easy. Okay, so to do the hit and trial, it becomes a lot more easier. So let's just put it back to 100, and then, oh my god, this is too much now. I guess my laptop, like, it's heated up too much. I've been using it since morning, so that might be the reason. Okay, so it's quite clear till here. So what's next? So the next thing we are going to do is the analysis part. It's very similar how we did previously, but things here are a little bit different. It's a lot easier than that, and it will take a lot of like very less time than what we did previously. So it doesn't matter the design file that you use. So once this is run, so make sure that you have already like for example here I'm using this file, right? So I have already run this file and I have the results captured here already. I can see the result. So let's see the result. Yeah, it's there, right? So for distance of 70 mm, I have not done swipe for all the distances, and just to save time before I like made this tutorial. But on the other hand, you have swipe values for all the distances, right? So that's fine. It's very simple to understand. Once you know how to do it for one distance, you can change the distance again and again. Now what I wanted to say exactly is the results must be there. You have to run the system already. Okay, so once you have run the file, the simulation is already run, the matrix is already captured, then only it will take very less time in Simplorer. So we are noting down the value of L as 15 microhenry, and we'll calculate the series capacitor C on the basis of resonance that will happen given by the formula omega L equals to 1 upon omega C, right? As you can see, I will open that up for you, and I have created an Excel sheet for that just to make myself easy. So I will put input resonance here, not the input resonance, the resonant frequency here, and angular frequency I have calculated as 2 pi f, and this gives the angular frequency omega, and I have used this here, right? So it's kind of a simple like Excel thing that I have done, and so I will put 15 here, right? 6.78, that's the frequency in megahertz, of course, and this is in microhenry, and I will get the capacitance in picofarad, right? So when I did this, as you can see, if I press 10, it will give me 55, but right now I need 15. So for 15 microhenry, which is the case right now, I'm getting 36.7. so let's round this up to 37 and see the result. Okay, so we are not randomly hitting at any place, because we have theoretical values and we know from theory that what we can do, right? So let's just go very near to the tuning value, that's 37 picofarad. This is a Simplorer. We have placed it, the model is placed here, which is already calculated, so no need to calculate it again. And now we need to do the analysis. Now there are two things here. As you can see, this is TR, that is transient, and if you double click on analysis, or let's just right click there and go to solution setup and add transient, add AC and add DC. So there are three types of solution setup that you can do. For now, let's do AC setup. What we are exactly trying to observe right now is the frequency splitting phenomenon, one, but more important than that, what we are trying to observe is where the resonance happens, because resonance is very sensitive, it happens at particular frequency. But now, as you can see, what our objective is to resonate at 6.78, because that's what we need, right? Though you can transfer power at any frequency, but we do not want that. We want to transfer power at 6.78 because we have designed our system at 6.78. This is not the complete system. You might have your inverter that is designed at 6.78 megahertz. You might have other like devices that might be designed for 6.78 particularly. So is the demand that we need to design things at 6.78, for instance. For now we assume that, okay? So maybe in a arbitrary way, when I put the value of C1 and C2, right now I have kept that at 100 picofarad, it's still resonating at some frequency, okay? But we do not know what frequency it is, and we do not want to be in that frequency. We want to shift that resonance from that arbitrary frequency which is happening right now to 6.78, and that can happen only when we change the value of C, because that's the only variable that we have right now. That's the only knob that we can rotate to bring that resonance to this particular frequency, and that we do by using the formula, theoretically the resonance formula, as simple as that, omega L equals to 1 upon omega C, and whatever we get from there, the value of C, for now we got that as we calculated from Excel. It was 37 picofarad. We are going to put the same value in the C1 and for C2, both the same value will be there, and then we will calculate. So for that we need AC solution type. So I guess you have understood why we need AC solution type. Here first you will see start frequency. This is the frequency from where the swipe starts, okay, and stop frequency is till this frequency the swiping will happen. Now our area of interest, or our range of interest, is actually our point of interest is 6.78, so our range of interest will be somewhere a little bit above that frequency and somewhere a little bit below that frequency. So let's start the frequency swipe from let's say from 6, 6 will be enough, 6 megahertz, till let's say 7 megahertz, because this will be inclusive of 6.78 of course. And the frequency step is the finer you want, is the better, right? So it doesn't make that much of difference in calculation time, but somehow, yeah, of course, the more fine you take, it will take a little bit more time, but that's fine. It doesn't make that much of difference. So let's just put 100, or we can even put 200. Let's put 100. Okay, 100 hertz. So it will be at a step of 100 hertz. It will linearize at a step of 100 hertz. So yeah, it will be a rough estimation of in that line 100 hertz jump will be there. So it's kind of coarse, and the AC sweep will be linear, of course. So leave it like that, and then just create that. So we do not want the transient for now, so I will delete that. So we are having our AC solution type, that's fine. We do not need optometrics here, right? But we need results. Now results, okay, let's go to results, and then create the standard report, rectangular plot, and let's see what we have here. So it's very same. We're doing the sweeping, the AC solution type is there. Okay, the primary sweep is in F. So okay, the x-axis is already set to F, that is the frequency. So just imagine the frequency, the x-axis is frequency already. It's frequency. It will go from 6 megahertz to 7 megahertz. Now what will be the parameter that we want to see on the y-axis? Then the height. What that height would be is nothing but the efficiency, I will say. Okay, so what will be the efficiency? The efficiency will be output by input, and output power by input power, obviously. So let's just do it, and be sure not to use decibel here, but instead of that you can use magnitude, or even you can say none. Okay, but since we are viewing the efficiency, let's use magnitude. So we have renamed it. It's output by input again. So V out will be first, and it will be multiplied by I out, and then divided by again I in and V in. So that's power, right? So this multiplied by magnitude of, so what it will be, I out. Okay, so make sure you are typing it right, dot I. Yeah, that's output for you, and let's just use parentheses properly, so it won't be very confusing to us, right? Okay, divided by, it will be magnitude of again V in. Make sure it's correct, V in. Okay, I guess it's right, multiplied by I in. Okay, I in underscore in. Yeah, it's right, multiplied by I. Yeah, and that's it. So this is the absolute value. What you can do more is use parentheses here too, an extra parenthesis that will save you from creating an error. Now what you can do is use another parenthesis. Okay, it's crazy parenthesis operation right now. Now this outer parenthesis is to multiply this whole thing by 100. Okay, and to see that in percentage value, it will be a lot easier. So create a new report, and it's created. Okay, so let's just close this. As you can see, it's a magnitude of B out multiplied by magnitude of I out divided by magnitude of V in multiplied by magnitude of I in, and that's basically nothing but power efficiency, right? So yeah, and this side it is frequency. So let's just go ahead and run this thing. So click on tutorial, and then change the value of C in and C out. It's 37, I guess, if you remember. So let's change to 37 so that it will be somehow nearer to the our desired range, right? At least it will fall in that range. We hope so. If not, then you have to do hit and trial again. But since it's supported by theory, it must be somewhere around that. So I have already changed the value, no problem in that. And let's just go to the simulation section here, and then you can see the analyze. Let's analyze, and let's just sit and observe how much time it takes. It obviously won't take much time like previously, so do not panic. But since my laptop is acting up, it might be a little bit slower than yours. So let's just wait. What happens? I guess there is some error. Okay. This one was very funny because we missed out a pin, right? So so my observation is a little bit poor today. I guess I'm hungry right now. So this was missing here. Yeah, sometimes this happens, right? And a small error, and we are searching for a like big elephant somewhere, and it turns out to be an ant that's causing the problem. So let's just clear this message and see. Let's do it again. Simulation, analyze. And view the result. Okay. Okay. As you can see, this is it. So this is 100% that you are getting here. This is the 100% efficiency, you can say, at that particular frequency. So where is 6.78 megahertz then? Where is 6.78? Can you say it? I can't say it. So what you can do is right click, go to marker, add marker, and then just drag around the curve. And if you can see at this point, I don't know if it's visible or am I blocking it. Okay, at this point, if you can see, that's the x-axis value. So just drag around the curve and locate 6.78 exactly. Okay, so just check at this point. So I will go and search for 6.78. I guess it's very near. Oh my gosh, it just missed that peak. So yeah, it's very near. It's very near. It's 6.78. Okay, it's here, 6.78. I will click and then the marker will be created. Okay, and once the marker is created, as you can see, the corresponding value is 92.89% efficiency, and that's actually pretty interesting. It's working fine, right? So yeah, you are transferring quite a good amount of power. We reached very close to the peak. That's because of the theoretical value, and the difference is because of the parasitic values that are involved in simulation, because it's very real in ANSYS. That is why. Now what is this is happening at a distance of 70 mm, remember, because it was very static at 70 mm. I created that design file exactly at 70 mm. I ran that at 70 mm. Now what if you want to check at other distances, right? So let's say this is enough for me, 92% efficiency is enough for me, for instance, but I want to check for different distances. So, and let's say my model consists of different distances, like I have done the simulation for like number of swipes, right, for 70 mm, for 110, for 200 mm. Now I want to change that in Simplorer. What I can do for that? So for that, go to the circuit first. Here, double click. Once you open the circuit, click on the model, and you can see few things here. The DISTT is the distance swipe, or the distance between the TX and RX coil, that is been taken into consideration, and the value is 70 mm fixed value. Okay, I can change the value manually too, but what will happen is, as I previously told you, it will take a lot of time to calculate that, reiterate the whole thing in the simulation, and then bring it back to the matrix, and then put it in the model and run Simulink, not Simulink, the Simplorer again, the circuit again. So that will take a lot of time. But since you have already calculated those values, 200 mm, let's say you have already calculated 200 mm, solution is already there. So what you can do is, you can change it from here. Put that value which you have already calculated. Let's say 200 is already calculated and you are very pretty sure about that. Put that value here, and then what you do is you override. Okay, you do not leave that, you do override. So once you override, do it 200 and you do override. That's how you do it, right? Similarly, you want to change the current, you do same thing here, but do not forget to override. And then once you do that, apply and then rerun the circuit. Okay, that's pretty as that, right? So you will find the curve that we just now we were observing, it's for 70 mm. Now your curve will be very different because it will be for 200 mm, right? So yeah, that's the concept. So just I will cancel it because I do not have 200 mm of distance. So where were we? So this was the result, right? And 92 was pretty decent, but I want to move this cursor to the top point here somewhere. I want 100% efficiency coil to coil, at least in simulation, right? In hardware, that's almost impossible to do, because when we do it in hardware, there are a lot of things that come into play. When we keep the WPT coil, it actually interacts with surrounding. The table that you have kept, there will be dielectric losses. If you place metal things in surrounding, in periphery of that, there will be eddy current losses, and it depends on frequency. And there will be particularly there will be the loss inside the wire, that is the eddy current loss, as well as the skin effect, right, because of the higher frequencies. So skin effect will come into play, and obviously you can't omit that just by using standard conductors. Standard conductors are solution as far as we can do, right? But even in standard, we can't go to that simplest strand, and for 6.78 megahertz, the strand needs to be very, very small, like in diameter, and that is just impossible to build. So considering all those things, 100% efficiency impossible, but 90% efficiency very, very possible, right? So coil to coil efficiency is always somewhere near 80 to 90%, to 95 even sometimes. So it all depends on what kind of frequency, what range of frequency you are running that thing on, and plus obviously the kind of wire you are using, the kind of environment your hardware is in. But for now, it's simulation, right? So at least in simulation, we want 100% efficiency, because we have considered zero losses, we have not considered the eddy current loss, we have not done that solution, right? So we know the losses must be zero. So yeah, so 100% is achievable. So don't be don't feel very shocked when I say 100% efficiency. It's very possible in simulation, and we can do that. So to do that, now we need to shift that marker to the left, right? Now to do that, we will change the value of C, of course, and I guess if I'm not wrong, I need to increase the value to shift it to the left. So to shift the marker to the left, I need to increase the value. Let's go to 39, and if it goes too much to the left, then we will again decrease the value. So this is the hit and trial, and here the variable comes handy. So I just changed so easily, right? It takes like 2 seconds to change that thing, and I will press analyze, and let's just wait. Well, let's try this then. What we can do now is, because the difference is very, very less, let's increase it by slight decimal. Okay, let's say 0.25. So let's do another trial at 37.25 and 37.25 because it's very less difference, so I guess that will be okay. Let's wait and see what the results will be. And we have moved farther away from the point, so this is not what we desire, right? So what we can do here is we need to decrease it and decrease it very slightly, because it's very much sensitive right now. So let's go and do the reverse. So it will be 36.5 and 36.5. let's just see what happens. Okay, oh my god, this is taking a lot of time because it's very sensitive right now. It just skipped the peak again, but this time towards the left, so we have to go a little bit up again. So you understand what we're trying to do, right? So I'm not doing it now, it's too much, right? So I'm satisfied with 90% efficiency for now, let's say. But if you want 100, because it becomes very sensitive to reach that peak and maintain that peak. And further there's another thing that I need to mention, because this is not practical. Well, it gives an idea of how much your capacitance should be when you're designing a real circuit, but it's not always the case that you will find that exact value of capacitance for your circuit in hardware. So that's the difficulty there. You won't find that exact particular, like for now what we're doing to achieve 100% efficiency. Let's see what we're doing. We are putting like the values in picofarad level. Picofarad is already so small, right? It's already very small. You will, although you find picofarad, 1 picofarad, 2 picofarad, you will find every variety of capacitor. That's not a problem. But see what we're doing. 36.5, and that's skipping. Now what we'll do is you will do 2.5 and you will do 2.567, something like that in decimal point. Now in market you are not going to get that capacitor for sure. Okay, so there's no point in tuning the circuit to so many decimal levels and then you're saying that okay, I reached 100% efficiency. That doesn't matter. So when you're working in hardware, how much close you can get with what hardware you have, right? So what is available in the market, you have to see that. So it might happen sometimes that it's not always about capacitor, because you can't change things there. So what you can change on the other hand is you can change the inductor, right? Because you are the one who will design the inductor, right? So change the length of it, play around the inductor's value. So it's a very conditional kind of thing. It's very situational kind of thing. You have to observe the things, what is happening with you, or what kind of limitation you have, what constraints you are playing with, right? And then decide. And this peak that you are trying to reach might not be reachable sometimes, if you are talking practically, but in simulation it is obviously reachable. But for now I'm too exhausted to maintain that peak and to tune this value. So you do that for yourself, right? Reach 100% efficiency. It's very possible, but it's very sensitive, so you play around with the decimal digit. Now you have got the range, right? 36.5 is coming towards left, 37 is going towards right, so somewhere between that, play around that, you will reach that level. And you can see two peaks are there, right? So this is called frequency splitting phenomenon in WBD. It's quite common. So if you want to know the science behind it, the physics behind it, then you can watch lectures of Sam Benkov, I guess, if I'm not wrong. His professor Sam Benkov, and it's fascinating. Yeah, he has given a very fine lecture on WPD systems, like the working of the system. So you can watch that lecture. And okay, don't be confused about this. I don't know, it's called bifurcation or frequency splitting, I guess, frequency splitting phenomenon. So that is everything about the AC parameter sweep that we did. It's parameter sweep actually. So the AC solution type. What about the transients then? Transient is also pretty important. And transient, as let's see what transient is. So for now I'm not going to delete this, but rather copy it, right, and then paste it here. So it's just a replica of that, but I will change the solution type to transient, and then we will see how the transient performs and what things we can observe from transient. Okay, so let's go and delete the AC solution there, and let's build solution type at transient. End time here denotes up to that point simulation is going to run, because it's transient, it is not that much big, right? So let's keep it very small. Millisecond is quite huge for us. Okay, let's go to nanosecond. I guess nanosecond is enough. Okay, 10 nanoseconds, that's fine. So that will be the final final time till which our transient will run. Okay, and then the minimum time step and maximum time step. So the time step plays around sometimes from minimum to maximum it will calculate itself, but we need to specify the minimum time step. So it will try to play around with the minimum time step if possible. Sometimes if not possible, the simulator will try to play somewhere between minimum and maximum. So minimum time step must be very small, obviously in pico, because we have defined in nano. So let's define in pico. Let's define it as 1. Okay, and this as 100, and it will be pico. That's it. Okay, now we draw transient, and then now the solution type is transient. Let's build a result, rectangular plot. So now as you can see, the x-axis is already the time domain. So so this is particularly when you want to see the waveforms, right? So for the waveforms, what waveforms you can see? The input side, let's not see input side, let's see the output side, because it's 90% efficiency and it's working quite well, right? So in 90% efficiency there must not be a problem. So ultimate goal of WPT is to get in phase voltage and current on the secondary side, right? So let's see the output. Then you can select simultaneous two simultaneous values like V out as well as I out. I want both of them in one. So yeah, this works. And remember, the function is none because this is the waveform that you want to see. If you do magnitude, then the negative part will be clipped out. Okay, so let's create a report. Okay, so this is I out and this one is V out. Okay, so first we need to run simulation to see. Let's wait. Okay, the result is quite shocking, because what we did is we didn't allow the transient to be long enough. So I guess my assumption of 10 nanosecond was very short. So let's just put that to millisecond or microsecond, and then let's repeat this process. Okay, so we'll go to TR. And we'll change that to 1 microsecond. Okay, and rest of the thing same. Let's get back to results and then run the simulation again. So yeah, so my decision of turning it to 1 microsecond was also not long enough. As you can see, there are only a few number of cycles and the transient is still on. So it has not settled to the steady state value, and because of which you can see some waveform are smaller and some are bigger. But with the passage of time, as the transients reduce, I guess in the 10th nanosecond or somewhere, the 10th microsecond or after that, it will be very natural and very easy, like it will be like you expect it to be. And but still, if you want to check the phase, as you can see, it's overlapping. That's because it has exactly the same phase, and because of that it's overlapping. The red one is current, the output current, and the and this one blue one is output voltage, and they are exactly on same phase. That means our objective is completed, right? They are in phase. That is what we want for a load resistance, of course, because our load resistance is 10 ohm and that's resistive load, right? So and the power transfer is happening quite well. So now if you want to see or just let's say if you want to know how much exact value like in data table the power is being transferred, right? In data table values, corresponding values in tables, if you want to see that, then instead of creating plots, what you can do is you can create data table like previously we did. So instead of doing that, create a standard report, create data table, right? And from here you can calculate the output voltage, sorry, not output voltage but output power, right? So what we'll do is let's just we can use magnitude also, but let's not use magnitude right now. What we can do is multiply it by I out. Okay, so this is the output power dot, this is the output power, right? So this is output power, and then we can also use wattmeter instead of these voltmeter and ammeters, and directly have those values here, because once you use wattmeter instead of these two meters, in this option here somewhere you will see the wattmeter output as power. So it will directly compare power, and that will be a lot easier for you to see the input power and output power at once, right? So create a new report and close. So this is going to give you the power, right? This is multiply, when you multiply these two quantities, this is giving you a power. And now when we see this, this is in time domain. So this is in time domain, which is not what we want, to be honest. So if you want to see like in time domain, there will be one peak, and that peak value will be somewhere around, as you can see, it's somewhere 0.7, right? It's watts, it's 0.7 watts. So I'm not sure. Okay, it's not 0.7, it's 4 point something, it's 4.3 I guess. Okay, oh no, it's actually increasing, because the transients we presumed transients were not completed. Actually it never reached steady state, so once it will reach steady state, I guess the value will be different. So particularly this is not what we want, because time domain is very tricky. Yeah, you can look with time domain also, but it will be a lot easier when you will observe these values with the AC analysis. In AC analysis, if you do this, that will be a lot more easier. So you need to create result here and do the same thing, right? So I guess that is all, because our objective is quite fulfilled here in simulation. So once we do these like whatever we did right now, we actually saw, is it in phase? We can actually see even the we can see power directly if we use wattmeter, and more concerned we are with the efficiency of it, and we already watched how efficiency can be maintained by tuning, right? So yeah, now the next step is implementing these things in hardware. That's it, right? This is all that we wanted from ANSYS, at least, right? So now what we can do to like take it to next level is we can go and simulate coils, but this time not in magnetostatic, but let's do that. What we can do is we can do that in like eddy current setup, and because eddy current will calculate all the eddy current losses that are involved in that coil. It might be of number of reasons, but I'm not pretty sure about the skin effect, but as far as I know, maybe skin effect is considered in eddy current loss. So but I'm not pretty sure about that. So but anyway, losses are considered in eddy current losses when you like turn the eddy currents loss on, right? So you need to specify yeah, you need to calculate losses, and then that solver will give you that ability to see the losses, but it will take a lot of time. So if you want to do that for your real project where your coil might be a lot bigger, actually I tried it sometime before. It took me almost a week. So I ran that in my laboratory for day and night. Maybe the frequency sweep that I did was too much, right? So the steps that I was taking was too much. So what you can try is, at least if you're trying in a practical circuit, the same number of circuit, like the size of circuit is very practical, you are using 200 like diameter of coil and all these things, then please make sure that when you do frequency swipe in eddy current loss solution, while calculating the losses also in eddy current type solution, there you can use very few like frequency points, otherwise it will take a lot of time. For me it took 1 week in a very decent configuration, and it was almost impossible to check all those swiping parameter values. Like it's very hectic. Once the data table is generated, it's so much of data table there that you will find you will have no idea what to do with that data then next, right? So make sure you reduce those swiping parameters like instances to very few, like 10 or 20 or 25, not more than that. It will take a lot of time, at least 2 or 3 days, even in that much of data points if you create. So if you're not getting what I'm saying, you can try eddy current loss and try to turn on the loss calculation, and then from result section you can actually see the losses also in watts. So you have your total watts that you can calculate from your wattmeter arrangement in the primary and secondary side, and then you have the losses calculated already, so you can subtract that and you can find the net wattage of your system, right? So how much is being lost and what will be your efficiency. Of course that efficiency matters, because practical efficiency will be somewhere near to that efficiency, and not this efficiency what we have calculated, because this is very much ideal case. 100% efficiency is not possible. And if you want to know the practical way of doing it, then eddy current solution that we discussed earlier is the right choice, and the process you will repeat is very same till here, and your objective gets completed exactly at this point, and that's it. Now you can try with different kind of coils. You can try with a little more complex circuitry. Maybe you can use DC like converter, I mean AC to DC converter, that is a rectifier on output side, and then test on AC load or something like that, right? Battery load, you can use battery load. You can do a lot of stuff, but it will take time. This was the simple test circuit, but it will take time if you consider practical circuit application. You can create inverters on, like inverter on one side and converter on the other side. So this can go on and on and on according to your need and application, but the gist is same and the way to do it is same. And that ends our tutorial session on wireless power transfer system. Especially that is very much based, this kind of design are very much based typically for electric vehicle charging systems, for the charger that we designed. So I guess I'm very hopeful that this was very fruitful to, like, if not to everyone, to some of you. Yeah, and I know that a lot of you had a little bit different kind of projects, though I was not available at that moment to help you, and it's not even possible to help everyone out, right? A lot of queries were coming in. Some were saying transformer design, some were saying a little bit different cylindrical designs or something like that. So if I can relate to those projects from whatever I know, I will obviously try to help. If not, then I will communicate the same, that I can't do that at that moment. If I'm engaged and if I'm busy, again I will communicate that, but at least you can try and bring something to me, and then I will just see how much difficulty level is there, how much new learning is there, whether if I can dedicate that time to you or not. So yeah, if I can, I have already helped few people, so that's the way that we do it, right? So I'm not assuring that I will help each and every one of you, but again, it all depends on what you bring on to me, and if I can work out with you. It's all like depends, right? It's situation. So let's see how it goes, and in upcoming future maybe the topic will be a little bit different, but I will keep on updating you guys. And do not forget to subscribe to get like future videos, updates about future videos. And yeah, like the video if you like if you have learned something, then please do not forget to like, and do not forget to subscribe, because that's what motivates me and motivates a content creator like me, right? And thank you for your patience, thank you for learning, and thank you for being with me all these sessions in this WPT session. Thank you. Have a good day. Bye bye.